The Generation 2 radial CVT was designed based on the very successfully tested first radial CVT, which broke the 90% efficiency barrier, which now serves as a benchmark for further application development. The concave and convex discs of the Generation 1 radial CVT were replaced by two flat discs, which resulted in the elimination of the combining planetary system required in the Gen 1 design. Flat discs are also easier and more cost-effective to manufacture. In the Gen 1 design, ratio adjustment was dependent on the convex and concave discs, while in the Gen 2 design, ratio adjustment is done in a direct fashion via a ratio spiral cam. This feature also allows for increased ratio shifting speed while providing precise control over the position of the three traction drivers. In the typical Gen 1 design, the ratio range can be extended to about 4.7, which is sufficient for small vehicles. However, larger vehicles, typically passenger, hybrid or ICE, internal combustion engine vehicles, require a ratio range of up to 10, which typically include the current 9 and 10-speed automatic automotive transmissions. The challenge for current commercial CVT as well as for radial CVT is to extend its basic range to a ratio range of 10 in a synchronous way and ideally without any power interruption. Currently, such dual-mode synchronous systems are realized by utilizing a planetary power split configuration with a downside of multiple wet clutches, as well as circulating power and torque, which has a negative effect on transmission efficiency. The Gen 2 radial CVT solves the problem by utilizing a three-mode synchronous system in which the second mode is a direct drive bypassing the variator and therefore represents a very high efficiency mode. While the second mode is engaged, the variator can shift to the required ratio range N to allow for synchronous shift. This three-mode synchronous system is realized with a single dog clutch with multiple positions, which simplify the selector automation very significantly. As with the Gen 1, input to the Gen 2 is via a central bevel gear driving three bevel radial shafts, each driving a drive with red traction drive rim. The drivers can freely slide in the radial direction. The input shaft is hollow, the purpose of which is explained later. Each driver is surrounded by the adjuster structure. The adjuster includes an up and down cam on each side, and on the inside has a roller on each side. The rollers regulate the radial position of the driver, and the up and down cams are engaged by the ratio spiral to regulate the radial position of the adjuster. The three adjusters slide in radial slots in the variator body, thus controlling the radial position of the drivers. Two ratio spirals, one on each side, is mounted concentrically with the input shaft. Three spiral cutouts engage the up and down cams of the adjusters in order to adjust the radial position as the ratio adjuster is rotated. The ratio spirals are driven by a gear system from the ratio shaft, which is driven by some low power control means. The most likely is electric. The drivers drive a front and rear flat disc via line contact between their red rims and the disc faces. The front and rear discs are coupled together via bevel coupling, gear engaging a bevel ring gear on each disc. The rear disc serves as the output to the Gen 2 radial CVT. The current Gen 2 radial CVT design includes two ratio spirals, one on each side, in order to provide a balanced shifting force on the adjusters. Prototype tests might prove that only one is needed, and simplify the design even more. The Gen 2 radial CVT in this configuration is ideal for EVs. The Gen 1 first prototype tests already produced transmission efficiencies between 85 to 90% through its ratio range, and the Gen 2 is expected to significantly improve on this. The central bevel gear system may consist of spiral bevel gears or zero bevel gears. These gears are widely used in the industry and have been proven to have a mechanical efficiency above 98% while running silently. The gear specifications here are provided for reference only to get a perspective of size and torque and present gears from a German industrial gearbox manufacturer. An additional benefit of the Gen 2 radial CVT is that the central bevel gears drive 3 radial bevel gears and therefore handles 3 times its rated torque, while it is only necessary to design the central bevel gear for 3 times the normal revolutions of that experienced by the radial bevel gears, assuming a 1-to-1 ratio. In order to achieve a 200 Nm input torque with a 3-to-1 to 1-to-1 ratio range, the traction drive parameters are as follows. The drivers have a 58 mm diameter, driving the discs with a 5 mm long line contact from a disc radius of 174 to 58 mm. The total clamping force generated via mechanical springs is 38 kilonewtons, which results in a maximum Hertz contact stress of a very conservative 2.1 gigapascal in the 5 mm traction drive line contact. The simulated traction drive interface results in a predicted 95.5 to 97.5 traction drive efficiency. Prototype tests on the Gen 1 radial CVT have produced slip results of 2 to 2.5% slip at maximum traction coefficient, which supports the above prediction traction drive efficiency. In transmission applications in the automotive industry, in hybrid and pure ICE applications, the current norm is a ratio range of between 9 and 10, which is currently implemented via 9 to 10 speed automatic and dual clutch transmissions. The radial CVT configuration has practical limits, which limits the ratio range to around 4.5 to 5. Therefore, to meet above ratio range, a multi-mode synchronous system is required. Synchronous modes refer to the shifting or engagement of components rotating at the same speed when changing from one gear system to another. Synchronous mode shifting can be done very fast since all components rotate at the same speed, resulting in minimal power interruption when done via dog clutches. When engaging and disengaging clutch packs are involved, the clutch action can overlap and power will not be interrupted at all, as is done in dual clutch and automatic transmission. The animation presented the addition of a minimal number of components to the Gen 2 radial CVT variator in order to generate 3 synchronous mode transmissions with a ratio range of 9 and beyond. The ratio range of 9 is chosen for simplicity's sake, since with a ratio range of 3 in the variator, a ratio range of 3 squared equal to 9 is generated with a dual mode system. For example, a variator ratio range of 3.31 will result in a 11 ratio range. In the synchronous 3-mode system, the front and rear discs are coupled by a coupling shaft via a gear on the intermediate shaft, thus replacing the coupling gear in the previous Gen 2 variator. A single selector, similar to those found in the dual clutch transmissions, is used to select low, direct, and high synchronous modes as described in the following slides. In the multi-synchronous mode, Gen 2 radial CVT hollow input shaft is coupled to a solid input shaft that extends to the selector, while the other end is coupled to the power source, typically an ICE via an automated dry clutch. In the low mode, the selector couples the rear disc to the output shaft and the variator can shift from there. When the variator reaches a 1-to-1 ratio, the solid input shaft will rotate at the same speed as the output shaft. The direct mode can now be selected as described in the next slide. In a synchronous shift, the selector couples the solid input shaft to the output shaft to create the direct mode. This represents a fixed ratio, direct coupling between input and output shaft that bypasses the variator and results in the highest efficiency. While in the direct mode, the transmission control system can determine, given the driving conditions, to which mode the transmission will select next, which is either low or high mode, and the variator therefore has ample time to adjust its 3-to-1 or 1-to-1 ratio accordingly. This strategy is similar to those used in a DCT transmission. Assuming the vehicle will continue to accelerate, the variator will adjust to a 3-to-1 ratio. With the variator in this 3-to-1 ratio, the high gear, which can freely rotate around the output shaft, will rotate at the same speed as the output shaft since its fixed ratio from the rear disc to the high gear is 1-to-3. The transmission can now engage high mode as described in the next slide. In order to select high mode, the selector couples the high gear to the output shaft during a synchronous shift. To complete the ratio range, the variator now adjusts from 3-to-1 to 1-to-1 to further accelerate the vehicle. The selector and dry clutch can be powered or controlled by any means similar to an AMT or DCT transmission. The front and rear discs are clamped together by clamping springs, while provision is also made for variable electric clamping, which can have a direct relationship with the input torque to minimize losses and increase efficiency. In a high-end multi-mode Gen II radial CVT, a dual clutch version can be configured as follows. The hollow input shaft is coupled to one clutch and the solid input shaft to the other clutch of the dual clutch, and therefore the solid and hollow input shafts are not coupled together as in the case with the previous configuration. The dual clutch can be identical to the dry dual clutches found in commercial dual clutch transmissions. The solid input shaft is rigidly and permanently coupled to the output shaft, and therefore the selector is only used to select low and high mode. Therefore, in this dual clutch version, power interruption is eliminated completely by clutch overlap in the dry dual clutch while shifting between low and direct mode and between direct and high mode. This slide represents the Gen II multi-mode radial CVT in a suitable casing that can be realized in 3 pieces. In order to emphasize the compactness and power density of the Gen II multi-mode radial CVT, the following are the parameters for an inline transmission configuration with ratio range of 9 and input torque of 200 Newton meters. The diameter is 280 millimeters, while the variator is 160 millimeters wide and the multi-mode selector is 105 millimeters wide, thus a total width of 265 millimeters. The weight is 28 kilograms and excludes the automated clutch or dual clutch as well as the selector control and oil. This inline configuration can easily be configured for a front-wheel drive or transaxle configuration. The radial CVT development is a very recent development and a brief history is now provided. A PCT application on the radial CVT configuration was filed in 2016, and this PCT patent application number WO2017143363 was granted in February 2017 without any modification to the claims. A MATLAB-based traction drive simulation based on a widely used traction drive model was performed during 2017 and predicted traction drive efficiencies between 95 and 98% by using Sanotrack 50 and 35A traction fluid. The first prototype was designed and manufactured during the second half of 2017. The first prototype was tested in October 2017 and again in 30 January 2018 at the University of the Witwatersrand in South Africa. In the second quarter of 2018, the Gen 2 design was completed to provide the basis for pure EV applications as well as high ratio range ICE and hybrid applications. The Gen 2 variator is also ideal for industrial applications. The test results were very encouraging, breaking the 90% transmission efficiency barrier, while peak efficiency and efficiency consistency rivaled current production and development CVTs as presented in the graphs below. The Gen 2 radial CVT was designed to, among other advantages, increase the transmission efficiency even further.